Okay, today's lesson is on simple harmonic motion. You're going to be able to describe examples of oscillations, define the terms displacement, amplitude, frequency, and time period, be able to define simple harmonic motion, and state the defining equation. We'll start by defining the term oscillate. So to oscillate is to vary position between alternate extremes within a definable time period. Let's have a look at some examples of oscillations. So this is the simple pendulum, a column bouncing up and down in water, air track slider, sliding backwards and forwards on an air track, it's got elastic bands attached to each end, and a weighted spring bouncing up and down. Let's look at some of those terms we said we were going to define in the objectives. So a cycle is one complete oscillation. In terms of a circle, that's 2 pi radians. Here we see a pendulum starting in the equilibrium position. It moves out to the side, it moves back the other way, and back to the equilibrium position. One cycle. Our next term is equilibrium position. So this is the rest position of an oscillating system. Here you can see the mass on the spring in its equilibrium position. Amplitude is the maximum displacement from the equilibrium position. Here we see the spring moving from its minimum displacement position through the equilibrium position to the maximum displacement position and back again. The maximum displacement is the amplitude. The time period is the time for one complete cycle. And symbol is T. The frequency is the number of cycles in 1 second, measured in hertz or per second. The angular frequency, omega, equals 2 pi f. This is something you might recognize from circular motion, and we'll understand more about what it has to do with simple harmonic motion in the next video. So have a look at an example. A mass on a spring completes 10 oscillations in 8 seconds. What is the angular frequency? So omega equals 2 pi f. The frequency is 10 over 8, 10 oscillations in 8, which is 1.25 hertz. Angular frequency therefore equals 2 pi times 1.25, which is 7.8 radians per second. So the simplest type of oscillatory motion is simple harmonic motion. And the mass on the spring is a good example of simple harmonic motion. We'll have a look at the definition of simple harmonic motion and see why it's such a good example. The definition of simple harmonic motion is that acceleration is proportional to the displacement from the central point and always directed towards it. When we pull down on the mass, the tension in the spring acts towards the equilibrium position. The tension in the spring is a force and it's causing the acceleration. When we release, the spring accelerates upward. When the spring reaches the top position, there is no longer any tension and the only force acting is the weight of the mass, and it's acting down towards the equilibrium position. So once again, the force and the acceleration are pointing towards the equilibrium position. While you watch this, think about the force, how it grows and diminishes, and its direction over the course of the motion. From this definition of simple harmonic motion, we have the equation of simple harmonic motion. The acceleration is equal to the negative of the angular frequency squared multiplied by the displacement x from the equilibrium position. Okay, that's the end of this video on simple harmonic motion. Next time we'll be looking at graphs of simple harmonic motion. If you missed anything or didn't understand it, flick back and watch it in the video or read about it on your book. Thanks for watching.